Okay, so here is an example problem of what integral test bounds would look like on an IB question. And so the first thing this said is to prove the limit as h approaches infinity of the integral from a to h of 1 over x squared dx exists and find its value in terms of a. Okay, so here we go. Limit as h approaches infinity. So basically they've already taken care of, oftentimes this will just look like infinity, and you have to change it to a b and make the limit as b approaches infinity. They basically took care of all that for you. So this is very similar to my integral bounds example where I explained how the bounds worked. So we're just going to change this to x to the negative 2, and to integrate that, we're just going to use power rules. So add 1 to the power times the reciprocal, and we're going to evaluate that from a to h. So this would be the limit as h approaches infinity. I'm just going to take a step to call that negative 1 over x from a to h. And limit as h approaches infinity, and we'll have negative 1 over h minus negative 1 over a. Now as h goes to infinity, this term is going to go to 0. So you end up with 0 plus 1 over a, or just 1 over a. Okay, so we found the limit and it is in terms of a. Now the next part says use the integral test to prove that this infinite sum converges. So it's kind of nice. This is a p-test. So, you know, if they didn't say what, it's already a p-series. We already know that this would converge. That's how we proved p-series to start with. But if it's asking you to use the integral test, you want to start by telling them you know the conditions. You're going to state that this is a positive, continuous, decreasing function. Okay, and then what you're going to do is you're going to integrate from 1 to infinity. And if the integral converges, then the series converges as well. Well, if you look, you actually already proved this in general up here. Okay, so I mean, if you're changing this, this would be the limit as, and I'm going to go ahead and change to h because that's what they had above, of 1 to h, and we normally do b. Okay, but if you notice, that's exactly what we had here. Okay, often these problems are connected and we forget. So we could do this all from scratch again, but we proved it's just 1 over a, which was the lower bound here. So this is just 1 over a, which for us is 1 over 1. Okay, so that's from above. Okay, so now all you have to do, it doesn't hurt anything if you didn't notice that, but it saves you a little time. The integral converges, therefore, the series converges by the integral test. Okay. And so that's that part, but it continues on. Okay, so it says, let L be the infinite sum from 1 to infinity, and they're telling you that the diagram shows the graph of y equals 1 over x squared. So that's what this is. And it's asking us to shade suitable regions on a copy of the diagram above. We're just going to do it on this diagram to show this. Okay. Now you have to know that the L is actually representing, it's going to be rectangles. Okay, it's going to be your sum, and your sum is going to be, your infinite sum is going to be represented by rectangles. Okay, now they're saying that this should be larger than this. So what that means is that your rectangle should be above the curve. Okay, so if you go and you want to try to start setting this up, then what you're going to do is draw rectangles that are above the curve. So let's just look at the first one. This is 1 wide, and the height would be f of 1. So the area of this is f of 1, f of 2. So there. Let's go ahead and draw some more rectangles. But here again, we know, since this is the rectangles are going to represent my infinite sum, I want them to be above this for this particular scenario. Okay, so all of these I'm going to draw are above using the left-hand endpoint. Okay, Okay, and so I'm just going to try to figure out what some of these down here are. If you look at this one, it's 1 wide. How high it is actually f of k minus 1. That doesn't really seem to be a splitting point there. But if I do this one, I can write it in. If I do this one, it's how high it is on the left-hand bound. That's f of k. Okay. And so if you look, this here is summing from 1 to k. Okay. So this part represents this part. Okay. And then what they're saying here is that my rectangles are above the integral from k plus 1 on. Okay. So let's look at what we're doing here. This part, okay, would give me the rest of it. That's actually going to be this part. Okay. So the way I would start this is I would say L is the summation from 1 to infinity of 1 over n squared. Okay. And so I know that I could divide that up from the summation from 1 to k, and then I could go from k plus 1 to infinity. Okay. And so here you have adding up from 1 to k, and then from here, this one is f of k plus 1 on. So I'm basically dividing it up into this region plus this region going on infinitely. Okay. And now what you know is your rectangles here are larger than the area under the curve, which would start from k plus 1 and go to infinity. And this part is just the actual function. Okay. And so that's what we've done. That's what we've shown by drawing in our rectangles and showing the different areas there. As far as shading in, what you could shade in is the actual rectangles itself. Okay, because that's what you're trying to find. That's what is representing your infinite sum. Okay, so let's see what they're going to ask us next. Looks like they're doing the same thing, just the other way. So let's see how we can do that one. Okay, again, now this is still from the previous page. Okay, so this is still, let's just go back real quickly, I tend to do that for us. That's still representing the infinite sum. Okay, so that is the summation n equals 1 to infinity of 1 over n squared. Okay. Now in this case, they're saying that my rectangles, which represent that infinite sum, are supposed to be below whatever this is. So when you draw this, you need to draw all your rectangles so that they're below the curve. Okay, now we do have an asymptote at 0. Okay, but these are finite. When we're making them be how high you are on the right-hand side, we're okay here. So these still have a width of 1. How high this first rectangle is f of 1, f of 2, f of 3. If you go over to this one, this would be f of k. That's usually my breaking point there. And then here, this would be f of k plus 1, f of k plus 2, and so on. So that's representing my sum. Okay, so what we're going to do is basically the same thing. Our limit is the same as, and they told us this, the sum from 1 to infinity of 1 over n squared. I'm going to divide that up into the sum from 1 to k, and then from k plus 1 to infinity. Okay, so again, we're going to do from here to here. All of those rectangles are represented by this, and then k plus 1 on are represented by these. Okay, the orange is a little sad there, I realize. Here, we'll do a little bit of purple. And then what you're going to realize is that your rectangles are below the curve. Okay, and so this quantity is less than if I left this alone. And something that's bigger than that is this integral from, and this one starts at k, I'm trying to replace from k plus 1 on, from k to infinity. And I left off the 1 over n squared here. Okay, and so we've got what they wanted as far as shading. You're shading the actual rectangles themselves, and you can see that they are smaller than the integral, and that's all on that one. This next part is only worth 2 marks. It says hence, so it must be using what I just did. Show that the limit is squashed between these two values. Well, in the last part, you actually already showed that the infinite sum, which is what they represent with L, was equal to the summation from 1 to k of 1 over n squared plus the integral from k to infinity of 1 over x squared. Okay, so that was already shown in the last 2 parts, but that's not my final answer. Okay, and I'd probably be flipping back, making sure I got all that. Okay, but in the very first part, we proved that this integral, if it was from, I'll just flip back for you. Okay, we showed that this came out to be 1 over a, where a was the lower bound. And so really, we already know that if we bother to go through all these steps, this is just going to come out to be 1 over k plus 1. And this part we can leave alone. This part we leave alone. And this part will come out to be 1 over k. That's from a, and we had already proved that in a. Okay, the grand finale says you're given that L is pi squared over 6. That means that that infinite sum is pi squared over 6. By taking k equals 4, use the upper bound and lower bound for L to find an upper bound and lower bound for pi. Give your bounds to 3 significant figures. Okay, now if you look up here, we've already shown this bound, and if we didn't show it, we can still use our result. Okay, so what I'm going to do is I'm just going to write that down here because I find it helpful to be able to just substitute in. And remember, you can always use the previous part. Okay, so we've got that. So now they're telling us that this L is pi squared over 6. They're not telling us how they know, but mysterious folks that they are, they know. Okay, and they're saying let k be 4. So this would be from 1 to 4 of 1 over n squared plus k is still 4, 1 over 4. And over here, k is still 4. This would be 1 over 5. This would be the summation from 1 to 4 of 1 over n squared. Okay, now you can put that on your calculator. I've already demonstrated that on another video. So if you put this on your calculator or substitute in 1, 2, 3, and 4 and add them all up, this will give you 205 over 144 plus 1/5. And this will give you the same thing, 205 over 144 plus 1/4. Okay, and so you have bounds for pi squared over 6. Okay, so basically what you're going to do now is multiply everything through by 6 and then take the square root. Okay, so if you just add these two numbers on your calculator, you're going to get 1169 over 720, and then 241 over 144. So first, to get rid of the 6, just multiply everything through by 6. That'll give you this result. And then you're essentially just taking the square root all the way through, square root of this, square root of this, square root of this. So you're going to get pi, and again I'm putting all this in on the calculator, is squashed between these two values. And they said bounds to 3 significant digits.